Hey class, it's Professor Adamson. This is Friday, September 11th, 2020. I hope all of you are doing okay. I know today's a sad day for just about all of us. So hopefully you're taking some time to reflect and hug your friends and family a little closer today, and hopefully we have brighter futures ahead for all of us. At any rate, we have a very complicated subject to get through today, and I want to keep this to 20 minutes. Each of these kind of little lecturettes, I think if they get much longer than that, nobody's going to watch them. So hang tight. You can watch this one multiple times. I'm going to be doing a lot of jumping around in slides from the slideshow that's listed under Unit 1. There are two slideshows listed under Unit 1, the intro one, which this one is from, and then Anatomy and Physiology, which will be the next and final one from Unit 1, okay? So hang tight. This one is about acoustics, okay? Now, acoustics is not really my favorite subject either, although it's become one. But at least on its face, acoustics has a lot to do with physics and a lot to do with science, and physics never was really one of my favorite sciences. I was more of a biology and chemistry sort of person. But I'm going to make sure that all of you at least understand the basics of acoustics before we move on to anatomy and physiology. Okay, so we need to make a quick distinction between acoustics and psychoacoustics. Okay, now on the 10 things sheet that I had each of you fill out, hopefully you kind of got that down, but just in case you didn't, acoustics has to do with science, has to do with numbers, has to do with math. Acoustics happens irrespective of us as individuals, whereas psychoacoustics has to do with us, with the unique kind of perspective that we bring to any situation. In other words, psychoacoustics requires perception. Psychoacoustics requires a brain. Psychoacoustics requires an ear. Acoustics doesn't. We can measure things acoustically even if we're deaf, and we'll get the same amount of sort of stuff involved, okay? Let's maybe kind of think of an easy distinction between psychoacoustics and acoustics. Now, acoustically, two pieces of music will look the same. Like if we measure them acoustically in terms of the frequencies and amplitudes for a piece of music, they'll look identical, right? But psychoacoustically, two different people will have very different perceptions of that music. One person may hear a piece of music and think, wow, that sounds really lovely, I like that. Somebody else may hear that same piece of music and say, oh, that sounds awful, it just sounds like noise, right? Maybe another kind of more easier distinction might be between a person who hears normally and a person who is deaf, okay? Now, a person who hears things normally, a loud sound will be painful to them. A very, very like 120, 130, 140 decibel sound will be loud, will be painful. But for a person who's deaf, that same sound will sound barely audible to them. It will sound like a pin dropping, right? Now, acoustically, the very same thing is happening, 140 decibels. But psychoacoustically, one person hears it as loud and painful, the other person hears it as barely audible, okay? I just want to make sure that you understand that distinction between acoustics and psychoacoustics, okay? So let's jump right into acoustics. Now, as I said, acoustics doesn't matter what our perception of the sound is. Acoustics just is what it is. Acoustics at its base is measuring frequency and amplitude. Frequency being the number of cycles per second, write that down please, cycles per second that an object vibrates. Intensity being the distance that any vibrating object vibrates, okay? So before we get into acoustics, we need to talk about what sound is, okay? Sound has a very long, kind of complicated definition, but if you can just think of sound being vibration, you will be fine, okay? Sound is vibration. Sound is vibration of objects happening all around us that when they vibrate at a rate fast enough and at an amplitude great enough, our ears pick them up. Objects all around us are vibrating all of the time, but it isn't until they get at an amplitude that's great enough for our ears to even be able to pick them up that we hear it as sound, okay? Sound, as it says in this slideshow, is vibration, okay? Now, for us to understand sound and its vibration, we need to think about we need to break it down, okay? For sound to occur, we need 4 different things. This is slide 20 on that first slideshow. We need mass. We need an object to be made up of stuff, right? You guys understand what mass is. Mass is matter. Mass is something that has molecules, and the molecules are made up of atoms, right? Mass is something that just takes up space, right? The next thing that we need is force. Force is a push or a pull on an object happening in a direction. Because it happens in a specific direction, that's a little 3D effect for you. Because it happens in a direction, it therefore has a vector. Vector just means having a direction, okay? So we need stuff and we need a force on that stuff, either a push on it or a pull on it, happening in a direction. The next thing we need, and these 2 concepts are a little bit difficult to understand, but if you remember Sir Isaac Newton and some of his laws, particularly his first and third laws, being an object that's in motion stays in motion unless acted upon by an outside force, or an object at rest stays at rest unless also acted upon by an outside force, we have the 2 kind of alternating concepts of inertia and elasticity, okay? Now hold that thought, because I think the easiest way for us to understand everything I've just described is, let's look at an object that actually vibrates, okay? This is slide 23, and if you actually play this slideshow, this has a nice animation thing that it took me forever to figure out. But this is slide 23, and what we see right here is what's called a tuning fork, okay? A tuning fork is something that a piano tuner uses. They boom, hit it, and then they get down and hit the key on the keyboard of the piano to see if the piano is in tune or not. And they'll either tighten the wire of the piano or loosen it, as the case may be, to get the piano either in tune because it's a little flat or in tune because it's a little sharp. Those of you who know a little bit about music know what I'm talking about. But let's see what happens. We have the tuning fork that has mass, and we will take that tuning fork and hit it onto the table, a force, right? And then the tuning fork, having 2 tines right here, it sort of looks like a football goalpost. Because of Newton's law, because of an object that stays at rest until acted upon by an outside force, boom, it goes into vibration. It is now in motion because of its inherent ability to obey the laws of inertia, okay? But because of the tuning fork's inherent elasticity, the tines of the tuning fork are pulled back the other direction. But because of inertia, back this way, elasticity, inertia, elasticity. So we've got a tuning fork that has mass. We exact a force upon it. Boom! Because of inertia, the tines go out. And because of elasticity, the tines come back. Inertia, elasticity. In other words, inertia just has to do with an object needing to respond to the laws of physics, and elasticity has to do with an object's inability to be permanently displaced by the force. In other words, because that tuning fork is made up of stuff, it's made up of atoms and molecules tightly bonded together because it's a solid, it's not going to go out and just kind of fall down, right? The tines of the tuning fork, because of its inherent elasticity, are going to go back the other way, and then go back the other way, and then go back the other way. The tines of a tuning fork, from rest to maximum point of excursion one direction, maximum point of excursion the other direction, back to rest, one cycle completed, okay? And the number of times that that tuning fork does this to this to this, one cycle, in 1 second, gives us its frequency. Okay, that's where we get the word cycles per second. So a tuning fork is a good example of an object that can create what's called a pure tone. Okay, a pure tone is a sound that vibrates at one frequency and one frequency only. There are very few objects in nature that can do that. In fact, the pure tones, in fact, the only things I can think of are a tuning fork and then my audiometer, which is right over here, which I'll show you in just a second. Pure tones are sounds that happen at one frequency and one frequency only, okay? Now, frequency is the number of times that the tines of the tuning fork do this in 1 second. So a very low frequency sound, low in pitch, will have a relatively slow rate of vibration. A sound that's very high in pitch, high up on the piano, if we're thinking of this like as a musical note, is going to have a relatively rapid rate, okay? Remember, the number of times that any one tine goes from rest, out, back, rest, that's one cycle completed. The number of times it does that in 1 second is its frequency, okay? Now, let's talk about amplitude. Let's talk about how loud a sound is. Amplitude is really a measure of distance, meaning how far the tines of the tuning fork go either direction. But how far it goes gives us the psychoacoustic perception of how loud the sound is. You can have two tuning forks of identical frequency and you hit one relatively softly, doo, and you hit one hard, doo. They are vibrating at the same rate. In other words, the cycles per second from here to here to here to here are identical, but the tines themselves are moving at greater distances, greater amplitudes, okay? The reason why it sounds louder is because each tine of each tuning fork knocks into an entire sort of sheet of air molecules that are right here, sending those air molecules into vibration back and forth and back and forth. In other words, when we hit a tuning fork, yes indeed, the tines of the tuning fork are vibrating at a frequency and an amplitude, but it is the air molecules that it knocks into that vibrate back and forth at the same or at least similar frequencies and intensities through the room until they hit an eardrum. The air molecules inside that ear canal get knocked into back and forth, hitting the eardrum back and forth and back and forth and back and forth. Okay? In other words, what we have just described is what's called simple harmonic motion, where a tuning fork, you can also think of simple harmonic motion as being a pendulum of a clock, a child swinging, a metronome on a piano, anything that goes back and forth, we can measure in terms of its frequency and its intensity, its amplitude, okay? I'm going to skip over compression and rarefaction because it's not really so important for what we need. I need to keep this short. But another way you can sort of think of this whole process happening, air molecules, it's hard for us to envision because air molecules are invisible, right? But if you want to sort of see how this process is sort of mirrored in something that you guys might understand, let's think of a slinky, okay? If I were to take a slinky, which hopefully you guys all know what a slinky is, it's a little metal coil. I think they still make those. They did when I was a kid. At any rate, let's take a slinky and I'll attach it over here to the wall and I'll pull the slinky taut. And once again, the slinky has mass, right? And I'm going to exact a force upon the slinky. Remember, a force is a push or a pull in a direction, right? So I'm exacting a force upon the slinky. We are going to see going down the length of the slinky. It looks like the slinky itself is actually moving, but all it is it's the energy moving through the slinky. The slinky itself isn't actually moving. Well, coils of the slinky are moving, but they're just moving back and forth. But it looks to the naked eye as though the slinky is actually moving across the room. It's a little bit like the wave. If you've ever been to a professional baseball game where it's not audience, it's the crowd, I guess, whoa, everybody stands up like that. And it looks like something is moving around the stadium, but nothing's actually moving. It's the energy is moving. Oh, and you see the entire stadium kind of standing. It looks like something's spinning around the entire stadium. No one person is moving any farther than from up to down. And if we were to keep that going up and down, it would look similar to a slinky where somebody's going dun 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 dun. Okay, I've only got 5 minutes left, so I need to keep this going. But what I've just described is essentially how sound is propagated through a room. In other words, we need mass, we need force, we need the objects that make up the objects within the space to obey the laws of physics, which includes inertia and elasticity. But an important way of sort of understanding this is in outer space, in the vacuum of space, we would not hear sound. Okay, why would that be? It's because in the vacuum of outer space, there are no air molecules to transmit that vibratory energy through the medium of space. In other words, something could explode and vibrate, but an astronaut several, kilometers or miles away would see the explosion but wouldn't hear anything. The reason being there are no air molecules between the astronaut and the explosion to propagate that vibratory energy through the medium space to be picked up by an ear. So in other words, that I think it's alien in space, no one can hear you scream. Well, yeah, no one can hear you scream because there's no air molecules to propagate that energy. At any rate, some of my references are a little bit old because I'm a lot older than you guys, okay? So let's talk about some other things about acoustics, okay? The pure tones are a little bit hard to understand because they are indeed pure tones. They're sounds that happen at one frequency and one frequency only. And as you guys know from, I think, the very first lecture, we as audiologists measure frequencies from usually 250 to 8,000 hertz. Hertz, as you know, are the units that we use for measuring cycles per second. Now, we as human beings have the capacity within our cochleas, within our organs of hearing, to hear sounds at a rate as slow as 20 hertz, 20 cycles per second, to as high as 20,000 hertz. That's so fast, I can't possibly do that. That's like hummingbird wing sort of fastness, okay? But we as audiologists are only going to measure pure tones from 250 to 8,000 hertz. We measure these 6 pure tones, 250, and then the next octave up, 500, the next octave up, 1,000, the next octave, 2,000, 4,000, 8,000. You'll notice that each of these double in frequency. Every time we have a doubling of frequency, we have the perception of having gone up in pitch 8 notes on the piano. Do, do, re, mi, fa, sol, la, ti, do, re, mi, fa, sol, la, ti, do, and so on. My singing is leaves a little to be desired today. But that's sort of what we do as audiologists. But as you guys know, sounds in real life do not happen at one pure tone. Any sound that I make, any speech sound splatters across a whole bunch of frequencies. But it's important to note that low frequency sounds are where most of the vowel sounds are at, and high frequency sounds are where most of the consonants are. Nasals and semivowels and glides happen also at low frequency, whereas all of the consonants that just involve articulation, t, ch, p, k, are mostly high frequency sounds, okay? But that's getting into a past lecture. I want to keep moving. You are going to, a couple other things I want to note real quickly. This is going to go a little over 20 minutes, but you'll just have to deal with it. A couple other things that I want to note. We can make what's called a waveform of a pure tone, okay? A waveform, rest, maximum point of excursion one direction, other direction back to rest. That's one cycle completed, okay? In other words, if this were 1 second happening here, okay, along this axis, we could count this 1 cycle, 2 cycles, 3 cycles, 4 cycles, 5 cycles, 6 cycles. This would be about a 6 hertz tone, okay? 6 cycles per second, okay? Now, this is by no means a high frequency sound and a low frequency, but from a waveform standpoint, you can see that the more peaks and valleys that you have in a 1 second time frame, the higher the frequency is going to be. Lower frequencies have fewer peaks and valleys. Higher amplitudes are going to go above and below rest at greater amounts. So the louder the sound is, the higher these peaks and lower these valleys are going to be. The higher the frequency, the higher the pitch, the more of these peaks and valleys in a 1 second time frame are going to happen. That's what a waveform is, okay? So some other quick things that I want to talk about: the velocity of sound. This is a very important thing to understand. Velocity just has to do with the speed of sound. In general, sound travels at about 1150 feet per second, about 350 meters per second. Now that sounds pretty fast, and it is, but it's not that fast compared to light, okay? Anybody who's ever been, once again, to a baseball game and you see the batter swing, and then a split second later you hear the crack, that tells you that light travels very rapidly. We see the perception of the batter swinging and hear the crack later. Thunder and lightning, same thing. You see the lightning flash and then hear the thunder a bit later, okay? And the later and later you hear the thunder, the farther and farther away the storm is, okay? One other quick thing I want to talk about acoustics is something that's called the inverse square law. This is slide 42, and this is a very scary looking graph, but I assure you it's not really that scary. The only reason why I bring up the inverse square law is to make sure that you understand that every time we double the distance from a speaker, let's say I'm talking and you take a step away and then take 2 steps away, the perception of sound in terms of its intensity, in terms of its loudness, in terms of its amplitude is lessened by an amount much greater than you would expect. Let's take a look at this graph here. This is a graph of maybe, I mean, it's just a fancy drawing, it's a fancified drawing. This isn't actually a picture, obviously. But you see the teacher here talking at about 60 decibels. And each time we go back a row in the classroom, we are reducing the signal by a greater amount than you would expect. You would think that the factor would remain equal, but as you go back farther and farther, it reduces it by a much greater amount than you would expect, to the point where this poor child in the very last row is actually hearing the background noise a little bit louder than the teacher. Now, it's not that the child in the back can't hear the teacher, but the background noise in the classroom and the teacher are sort of equal enough that the child's missing out a lot on what the teacher says. This is an important concept for those of you that want to work in schools, to know that there are lots of kids out there that are not doing well in class. It's just because they can't hear the teacher very well. The acoustics of the classroom, the number of kids that we have in classes nowadays can help explain that. Last but not least, in terms of acoustics, and this has been very rapid, this is slide 44, is the notion of resonance, okay? Resonance, okay? Resonance. Resonance basically has to do with when one object goes into vibration, a neighboring object feeds off of it, and it can also go into vibration. A good example of resonance is understanding with a guitar, okay? When I strum a guitar, the strings of the guitar are indeed vibrating. I'll go brum and strum the guitar. The strings of the guitar, just like the tuning fork, vibrate up and down at frequencies and amplitudes. The harder you strum it right, the greater the amplitudes, right? Brum, I strum the guitar, but we have resonance happening. The wood, the panel of the guitar, and the box of air, you guys probably know this, but a guitar has strings on top of a kind of a hourglass-shaped figure. It's a box of air. I strum the guitar just like this. The air molecules within that box of air and the wood molecules on the face of that guitar also go into vibration. We perceive the vibration of the strings, the vibration of the wood, and the vibrations of the air molecules inside it to give us the perception of it indeed being a guitar. If we were to just strum the strings and not have the wood and not have the box of air, it would sound very thin and tinny. Bling, plunk, bling, 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 bling. But because of the resonance of the other vibrating objects, you know, we didn't do anything other than strum the strings, but the strings being put into vibration caused a sort of resonant vibration of the box of air and the wood to also give us that sound of it being a guitar. Another way of thinking of resonance or sort of forced vibration, if you want to think about it this way, is, well, I'm doing a terrible job, but any of you who've ever had a bottle of soda, it's probably better with a bottle of soda, and gone, hoo, 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 what you're doing is finding the natural resonant vibration of the air molecules in the space of air from the top of the soda to the top of the bottle. Hoo, hoo, hoo. You drink some more of that soda, and now we got a longer column of air. Hoo, hoo, hoo. In other words, the more and more we drink and the longer the column of air is, hoo, 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 the lower and lower the resonant frequency is of that column of air. A similar thing happens here where I've got vocal folds that are vibrating, but it's due to resonance. The column of air above my vocal folds and the space of air within my mouth, we have air molecules also vibrating, resonating along with the vibration of vocal folds that give us the perception of ah, e, o, oo. My vocal folds, in that case, ah, e, o, oo, are vibrating at similar frequencies. You can hear the pitch being similar, right? Ah, e, o, oo. But it's because of what's added, the additive nature of the resonant vibration of the air molecules within my throat and within my mouth as I change the shapes and sizes of that make those unique phonemes. All right, I broke my promise and I went over by about 7 minutes. We have one last lecture for this week, which is anatomy and physiology, and then we'll be all done with, already done with 2 weeks of class, so good on all of you. Email me as always at pcadamson@yahoo.com. Thank you very much.